Welcome to our 12th lecture on parallel programming. Today's topic is MPI Input-Output, or MPI I/O. First, some basics. Now, in parallel applications, the need often arises to have coordinate parallel access to a file by a group of processes. And they have to access that file simultaneously or not, maybe non-contiguously or not. So there's lots of scenarios where you could imagine that it would be useful to have coordinated access to a file from different processes. So this means that the data may be distributed across the processes according to some partitioning scheme. Imagine like a big matrix that has to be distributed across all processes so that they can work on it. And of course, this should be done in a way that makes it efficient to access that file instead of just opening and closing and working on files using the standard POSIX file I/O functions. So this is the general picture we have in mind here. We have our MPI ranks, and they have a so-called logical view on the file, which means each rank only sees a part of the file or the part of the file that it's supposed to see and to work on. All the actual mapping on the physical file on the actual disks or the disk subsystem is hidden from the program and it's abstracted away by the library. Now, what does MPI I/O do for us in this respect? It provides a high-level interface to support this kind of data partitioning. It can transfer global data between the memory and the file, so this is called collective I/O. It supports asynchronous transfers and strided access, so everything you would wish for in an I/O interface for MPI. The means to that is MPI-derived data types. So if you don't know what those are and how they work, that would be a good time to refresh your knowledge about that, because MPI-derived data types are essential for how MPI I/O works. Now here are the principles. We'll go into more detail about this later, so this is just a course overview. An MPI file, as seen from the perspective of MPI I/O, contains elements of a single MPI data type, and this is called the E-type. Imagine it like something like MPI int or MPI double. It could also be a derived type. The file is partitioned among the processes using an access template, and this access template is called the file type. All file access transfer from or to a contiguous or non-contiguous user buffer. So the MPI data type is used to describe the access to the file, and all the buffering that needs to take place is taken care of by the MPI library. So the data type actually defines which part of the file a process is going to see, and what the buffer looks like that the local data from a local rank is going to be stored at. There are several different ways of reading and writing data that MPI I/O supports. There could be there are blocking and non-blocking variants, collective or individual variants, and also there are differences with respect to how the file pointers are handled. For example, you could have individual file pointers, so a separate pointer for each rank, or a shared file pointer that's always advanced whenever a single process, no matter which one, accesses the file. You could also access files using explicit offsets for one-time reading and writing actions. There's automatic data conversion. You know, this is a feature that was built into the MPI standard from the start. So it is possible in principle to run MPI programs with I/O on heterogeneous systems with different data representations on different parts of the system. And it is possible to read and write files that are interoperable with other programs that are not MPI based. So you can actually write a file that can later be read by some other program, for example, a standard POSIX I/O based program that doesn't know anything about MPI. The first step towards using a file is opening it and later closing it again. So here's the call in MPI to open a file. It's called MPI file open. It requires a communicator, and the call is collective by all processes which are part of that communicator. This appears like an unnecessary restriction, but we'll see later that it's quite simple to actually open files on single processes actually. There must be a file name, of course, and all the open calls in the communicator must of course open the same file, although the file name might be different. A mode is an access mode, just like with POSIX IO. You can specify different things here, and we'll come to that on the next slide. There's an info object of type MPI info that can be used to further specify some optimization flags and parameters in order to make the data access more efficient. And finally, there's a file handle, FH, of type MPI file pointer. And later, the open file will be associated with this file handle, just like it is the case with standard I/O functions. If you want to do process local file I/O, so if you want to open a file just by a single rank or process, it is possible to do that by specifying, instead of MPI com world or whatever communicator you put here, just writing MPI com self. And com self is a communicator that only comprises the current process, nothing else. Here's the list of allowed access modes. The first three are special because one of these is required. It's either read-only or read and write or write-only. All the others are optional. For example, you could specify that the file should be created if it doesn't exist, or an error should be flagged if it does exist, and so on. So you could go over these at your leisure. And of course, as is usual, such access mode flags can be OR together in order to specify more than one flag, like MPI mode write only, bitwise OR, MPI mode append would specify I want to write only and I want to write at the end of the file. In Fortran, this would be done using the bitwise manipulation function like IOR. So here's an example. I'm creating a file handle object, MPI file FH. I'm opening the file across the whole communicator, so this has to be called by all ranks in the communicator. The file name is some string. I want to create the file if it doesn't exist, and in write-only mode. For the info object, I'm here specifying MPI info null because I don't want to say anything about data access optimizations, and then I need the pointer to the MPI file handle. So this has the effect that all processes open the file at the same time collectively. As I said, if you want to open a file with a single process only, the order of events and the flags are the same, except the communicator, which has to be MPI com self. And of course, if you have communicators that comprise only a part of MPI com world, you can also use them here. So the only rule is open has to be called by all processes in the communicator. At the end of the program, usually close the file again. Of course, we should. All you need to specify here is the pointer to the file handle. It's also collective across the communicator in which the file was opened. The state is synchronized, so the standard specifies that all the data that might be buffered is transferred to disk storage, and the file handle is invalidated in a sense, so it's set to a special value called MPI file null, which means you can always check whether a file handle is valid or not by comparing it to the special value MPI file null. There's a flag in the A mode collection called MPI mode delete on close, which specifies that if the file is closed, it should also be automatically deleted. Of course, this is useful sometimes if you use the file for out-of-core computation. So you write part of your working set to a file in order to save memory. And then at the end of the computation, you don't need that data anymore. So you could let MPI delete it automatically at the end of the program. Of course, there's a rule. You will see later there are non-blocking file I/O requests and so-called split collectives, which are also a variant of non-blocking. And all outstanding requests of that sort associated with a file must have been completed at the end. So it's not allowed to close a file when outstanding requests are still waiting. So you have to finish these requests before you close the file. I've talked a little bit about info objects, and in our example, we set the info object to the special value MPI info null, which means you don't want to say anything about optimizations, but info objects can actually, in practice, optimize the performance of file I/O. An info object is a so-called opaque object. You don't want to know, you can't see what's inside this object. You only access it using well-defined functions. An info object stores key and value pairs. And what you use it for is you provide system-specific information via this info argument. So in the end, if you know the specifics of your system, it may lead to higher performance I/O. As I said, an info object contains key and value pairs, and of those keys, all may be ignored. So you can specify an info object, you can set any parameter that you like, but the MPI implementation is still free to ignore anything you say here. There are some reserved keys, we will come to that later, but implementations may provide additional keys. All keys and values in the info object are strings. So what MPI does with these data internally, you don't know, but the interface that you're using for these kinds of objects is actually string-based. If you don't want to provide any of the information, you just use MPI info null and be happy, and actually most users do that. So here's a little example of how you could use that. You instantiate an info object, MPI info. You have to initialize it, calling MPI info create with a pointer to this info object. And then you can add entries to an existing object by MPI info set. You need to specify the info object, the key, and the value as strings. As usual, the MPI standard is very thorough here. And of course, if you can establish an MPI info object, you can also delete it by MPI info delete. You can, instead of feeding information into the object, also retrieve information by MPI info get. So you specify a key and you get the value back, or you get a flag saying false if there's no value for that specific key. You can free an info object, so you can the internal memory that is associated with this object will be freed. And of course, there are length restrictions. There are predefined symbols, MPI max info key and MPI max info val, which specify how long keys and values may be. And of course, these are implementation specific. Here's an example for how an info object can be used to optimize I/O. These info objects are specified when you create the file, so upon MPI file open, and they must be the same for all processes, else the behavior is undefined. As I mentioned, it's only a hint. The MPI implementation is free to ignore the info object. For this purpose of striping, there are two keys that you can specify. The striping factor. Striping factor specifies the number of I/O devices the file should be striped across, and the striping unit, which is the number of consecutive bytes stored on one I/O device before the next is used. So if you know a little bit about parallel I/O hardware, you know that if you map a file to the actual I/O devices, and these could be I/O servers or disks or whatever in the background or the hardware layer, then there's something called a striping unit, which says what is the unit, the consecutive unit of data that goes to a single I/O device. And the striping factor specifies how many of these devices should be used. Now, depending on what the load on the file system is and what the usage scenario is, it could be useful and beneficial for program performance and for system performance to actually set these two parameters to other values than their defaults. And this is what the striping factor and striping unit keys do. Another issue with I/O is buffering. So in standard I/O, each process might access different I/O devices, and this can generate high load. Now, usually the operating system facilities provide buffering in the main memory of the process that reads and writes files, so that's usually a good thing. However, if you do parallel I/O, the operating system doesn't know that you're doing parallel I/O. All that it sees are processes doing I/O, and it tries to do its best to buffer these I/O data traffic to the best of its knowledge. However, if you know that you're in a parallel program, it might be useful to use so-called collective buffering. And this is what a typical system looks like. Here, for simplicity, I've chosen nodes with 4 processes, and each of these processes on those nodes is doing I/O, accessing the background storage. So how could we optimize this? And in MPI, there's a standard keys for the info object that can influence the buffering behavior. So it optimizes I/O for collective accesses. And the way it does that is it specifies so-called target nodes that are responsible for buffering so that the overall load to the I/O hardware, to the file system hardware, is reduced. So instead of every process doing I/O to the hardware, we have processes doing the work, doing I/O. Of course, those processes are placed on the nodes. However, there are specific target nodes which conduct the actual I/O operations on behalf of everybody else. And the number of these target nodes could be smaller than the actual number of nodes which are part of the communicator. So here are the keys associated with this behavior. There's this collective buffering key, which can be true or false. So you set it to true if you know that your application might benefit from the collective buffering. CB block size is a block size that says that specifies the chunk size in which the target nodes access the data. CB buffer size is the size of the I/O buffer used on the target node for this buffering facilities. Usually it's a multiple of this block size up here. And CB nodes is the number of target nodes. And using these flags, using these key value pairs, the implementation can try to optimize I/O and make sure that only this a limited number of specified target nodes actually do I/O, relieving the burden to the I/O subsystem. So here's an example for how creating and using an info object may look like. We're instantiating the object here. We initialize it with MPI info create. Then we want to specify that striping should be done over 10 I/O devices. So I'm setting the striping factor key to the value 10 in the info object. I want to enable collective buffering with 4 nodes. So collective buffering is set to true and CB nodes is set to 4. So this is how we set up the info object. And then the MPI file open call, this is the place where the info object is actually used to convey this information to the MPI implementation. So I'm calling MPI file open with this info object. Again, if I don't want to provide this information, I can just write MPI info now. At the end, I can call in MPI info free if I want to free the space associated with this info object. For reference, I included here a program fragment that queries the info of an open file. So it takes an open file, gets hold of all the key value pairs and prints them. So this is what you could get. You can go over the details at your leisure. Some interesting info we see here is that the collective buffering size is 16 megabytes and 1 node is used. The striping unit is 1 megabyte and the striping factor is 32. So these are the settings that are applicable to this file. Here's some miscellaneous file manipulation routines that I also won't go into detail about. So we can pre-allocate space for a file or resize a file while the program is running. We can query a file size, we can query the access mode, and we can actually change the file info object for a file while it is already open. All right, so much for opening and closing and specifying optimization hints. The next thing we need to look at is how the individual processes or ranks in an MPI program view the data in the file. And the central concept here is a file view. So a view is the visible and accessible data from a file, and it's not necessarily every single byte of that file. Each process can have its own view, and they can be different across processes. The view is described via a 3-tuple, a displacement, an E-type, and a file type. The pattern of the file type is repeated beginning at displacement. The view can be changed, and it's a collective operation. And the default view, if you open a file and don't specify anything, is a linear byte stream. So every process sees the file in the same way, and it views every single byte of this file. So the E-type, as I mentioned at the beginning, is the basic type that the whole file is made up of. The file type is the pattern that is repeated when looking at the file from the point of view of the process. So in this case, we have three E-types. Imagine it to be like an integer, for example, and we have two holes at the beginning. So the file type has a length of an extent of 5, and only 3 of these 5 elements are actually visible. And there's also a displacement. So for example, if your file has some header information that's not interesting for the process at hand, you can specify this displacement to skip over any of this information. And then the file type is just repeated until the end of the file. The visible and accessible data that the process actually sees is only the green part. And it sees this data in a consecutive way. The default file view, as I mentioned, is a linear byte stream with displacement 0, E-type is MPI byte, and file type is MPI byte. And this is the same for all MPI ranks. This means that the file, as shown here, is a sequence of bytes, and different MPI processes have the same view, and they have identical views, and they can view and manipulate every single part of the file. This may or may not be what you want. In simple situations, you can get away with that and manipulate the file the way you want it to be, but sometimes it's more convenient to actually restrict the view of processes on the file in order to do more advanced things. Here's an example of a custom file view. We have an elementary data type. Again, imagine that to be something like MPI int, or also derived data type. And we have 3 processes, 0, 1, and 2. The file type for process 0 would be 1 element and then 3 gaps. File type for process 1 would be a gap, 1 element, and 2 gaps. And the file type for process 2 would be 2 gaps at the beginning and then 2 elements consecutively. There could be a displacement. So I want to read and access the file only after this displacement in bytes, and then starts the actual content that the processes are able to see. And the colors here denote how the content of the file is mapped to different processes. So everything that's orange is mapped to process 0. And later, only process 0 will have access to these orange parts, only process 1 will have access to the blue parts, and only process 2 will have access to the purple parts. Now this is the magic of MPI I/O. The view of process 0, so if you do sequential I/O, is actually consecutive always. So process 0 sees a consecutive stream of E-types, and as seen from the original layout of the file, it would see elements 0 and 4. Of course, skipping any displacement we might have. Process 1 would only see bytes 1 and 5, or sorry, elements 1 and 5, and process 2 would see elements 2, 3, 6, and 7, and so on. This repeats across the whole file till its end. Again, here is a definition. Here are definitions for all these terms I have defined. I will not go into detail here. We mentioned most of them already. A couple of things you need to know. The E-type, of course, has to be the same for all processes. The file type can be different, of course, for all processes. That's the whole point. It doesn't have to be, but it can be. The view is specifies the accessible data of a file by a process, and it's defined by this 3-tuple displacement, E-type, and file type. Offsets, if you need to specify them, and we'll come to that in a minute, are positions in the file relative to the current view. So an offset is always something that's only valid as seen from a current view. In C, there's a special type for that, MPI offset. In Fortran, it's an integer of a specific kind. But the unit is always the E-type. So The offset is always given in units of the basic data type that you specified as the E-type. For example, if the E-type is MPI int, then the offset would be in units of 4 bytes. Here's how you set the view on an open file with file handle fh. It's a collective operation. The local and shared file pointers are reset to 0. We'll come to file pointers later and how they are handled. The E-type is an MPI data type as well as the file type, and they both must be committed types. With the E-type and the file type, you specify the actual view of the file it's just explained. The data rep string specifies the format that is used when the data is written to a file. It can be one of the 3, native, internal, or external 32, or it can be user-defined. We'll see something about that on the next slide. Of course, the E-type extent and the data rep must be the same on all processes. The file type, in principle, doesn't have to be the same as just explained. Disp is the displacement at which the actual view should start. It's an MPI offset in C or an integer of MPI offset kind in Fortran. And this is how you set the file view. The data representation argument deserves some comment. And here are the 3 predefined representations you can choose from in MPI-IO. The first one, called native, stores data in a way that's identical to main memory, which means it's the highest performing way of storing data because there's no reformatting or reinterpretation of the data. However, it loses interoperability, so it's not compatible with heterogeneous systems where parts of the system use different data, internal data representations. It's also not guaranteed here that this file is accessible from standard non-MPI programs. The second one is internal. It specifies that the data is stored in an implementation-specific way, so it's compatible with heterogeneous systems and type conversions will be performed. However, also there's no guarantee that these files are compatible with standard files written and read from C and Fortran. External 32 is what you would use if you're all for portability and compatibility. It follows a standardized representation, so the I/O operations are done so that what actually ends up on the disk is readable and writable from normal non-MPI programs, and afterwards it cannot be seen whether or not this file was actually coming from MPI. So this is what you do for full portability. This is actually what is recommended unless you actually know that external 32 has performance implications in your specific case. Here's a simple example of a file view and the code for it. So we specify it here for a single process. The view contains holes with respect to the original file. The original E-type was MPI int. Here's our file type for one process. So we have 2 ints and then 4 holes. So 2 MPI ints followed by a gap of 4 MPI ints. Our displacement will be 5 times MPI int and then followed by as many file types, as many 6 MPI int units as necessary to fill the rest of the file. The first step is to create a data type that actually represents the file type. So we need a data type object called E-type and a file type. Now, in order to do this, for this particular case, we're using the subarray type in 1 dimension. So the sizes array would be 6. This is the dimension of 1 dimension of the subarray, which would be 6 elements here. Subsizes would be 2, which is the actual used consecutive number of elements, so 2 ints. And start indexes would be 0 because we don't have any gaps at the beginning. Now then we call MPI type create subarray. The number of dimensions is 1. That's what the 1 denotes here. Sizes, subsizes, and start indices are the arrays that we just preset. The order is as in C, although it wouldn't matter here because it's a 1-dimensional array. The basic type, the E-type, is MPI int, and the file type is what we get out of it, and this has to be committed, of course, to make it usable. We have a displacement of 5 MPI ints, so here's how we calculate the displacement. Actually, that's not quite correct. We have to be correct, we have to use the MPI type size functions, but it works here in this way. The e-type is MPI int. So now we've got everything together to open the file on the communicator MPI com_world. This is our file name. And we want to create it if it doesn't exist, and we want to read it or write it. So MPI mode read write. The info object is not specified, so we need to say MPI info null, and this is our file handle. So this is how we open the file. After the file is opened, we can set the view using MPI file set view, the displacement, the e-type, and that's most important, the file type that we created here using MPI type create subarray. The representation in this case is native. And then later we can write to this file, and we'll come to that in a minute. So how do we actually access the data in the file after we set the stage by defining a view to the file? Now, there are of course a couple of functions that do what you want. We need to specify the direction, whether we want to read or write when accessing the file. There are functions for positioning file pointers, and the way this is done exactly is specified by the names of those routines. So for example, there are positioning routines which have an at the end, and they deal with explicit offsets, so stuff that has to be done, read or written at one particular place in the file. The standard functions without any positional qualifier always use individual file pointers, as you would expect from standard POSIX-based I/O. So every process has its own file pointer that gets automatically advanced whenever you read or write. And there are functions with shared file pointers, and they end with shared or ordered. And those have a global file pointer shared across all the processes in the communicator. And there are flavors for those depending on whether they are non-collective or collective. There's something for coordination, we'll come to that. Synchronization, for example, there could be blocking and non-blocking variants of I/O functions. The non-blocking variants follow the usual pattern that we looked at when dealing with point-to-point communication, so they start with I. And there are also split collective variants where you could have non-blocking behavior by specifying where the I/O operation begins and where it ends without actually having to deal with handles, as we have to do with standard non-blocking functions. And there's things you can specify in terms of atomicity, so atomic and non-atomic access, and I will not go into details here. So here's an overview of all data access routines. So the first categorization we use here is about the offsets, the positioning, so whether you use explicit offsets, individual file pointers, or shared file pointers. And across these categories, we have different variants with respect to synchronization, blocking, non-blocking, and split collective in all three categories. For example, if you want explicit offset I/O with blocking semantics and non-collective, you would call a function that ends in real, read at or write at. If you want collective semantics, then you would add _all at the end. If you want individual file pointers and non-blocking semantics, you would use an iRead or iWrite function for non-collective behavior, so individual, or with collective behavior, you would do iRead all and iWrite all. So the difference here would be that probably if you use the collective call, you actually want to do something from all MPI processes, then MPI has the opportunity to optimize the access. While with non-collective, it's actually, there's less opportunity for internal optimizations on the side of MPI. For shared file pointers, for example, there's an interesting variant, the collective ordered variant with, so this means that you can actually specify that the access to a file with respect to modifications of the file pointer should be ordered across the MPI ranks. So this could be important when you want a well-defined mapping of MPI file contents to MPI ranks. So here's the difference between individual file pointers and explicit offsets. So if you have individual file pointers, and here in this example, we show this with 2 ranks, then at the beginning when the file is opened, and we're dealing with a standard file view here, then process 0, say, does a read operation of 5 elements, 0 to 4, followed by a read operation of 2 elements, 5 and 6, while process 1 does a read operation of 9 elements, 0 to 8, and then followed by another read operation um, for another 2 elements. And those 2 file pointers, so the positions that the next read operation starts from, they're totally independent across these 2 processes. So they're really individual file pointers, and the behavior is what you are used to from standard POSIX-based file I/O. Now, explicit offsets deal with offsets that you specify when you do the reading or writing operation. So in this case, we chose to read the file at the beginning using a normal individual file pointer with standard POSIX semantics. So we read the first 5 elements, then the next 2 elements using a normal read operation. And then we choose to read 2 elements starting at offset 10. And this is something that's independent. So I specify an offset at which to read, and then the next read add could be a totally different offset. So here's how we deal with explicit offsets. The simple call is MPI file read add. The offset is specified here, and as I mentioned, this is where the reading starts, and it has to be specified in units of the E-type of the basic data type that the view is comprised of. Count elements of data type are read. Now, one important distinction from standard I/O functions is that the end of file condition can be detected by noting that the amount of data that was read is less than count. How do we get the amount of data? You use something that you already know from point-to-point communication. You use MPI get count. There's an MPI status object. That's the whole purpose of that. You specify that for MPI get count and the data type, and then the receive count contains the actual number of elements read. This means that the standard end of file condition is not flagged as an error. So this is an important difference in behavior. The end of file has to be detected by checking the actual amount of data read. Remember that these explicit offset routines do not alter the file pointer. So if you do the same call again, back to back, you will read the same data from the same place in the file. If you want something more closer to POSIX behavior, here's individual file pointer semantics, MPI file read. You read count elements of the E-type, and the individual file pointer is then incremented, automatically advanced to the next position using this formula: count times the number of elements of the data type divided by the elements of E-type, which means after the read operation, the individual file pointer of each process points to the next E-type after the last one that will be accessed. Okay, unless of course end of file was reached. Again, you have to check end of file by checking the amount of data that was read. So this is really very close to standard serial file I/O. Of course, reading or writing to a file is not the only way to manipulate the individual file pointer. Of course, you can call a seek function, MPI file seek, and it requires an offset with the usual semantics. And the last argument, whence, specifies what is actually how the offset is interpreted. So, for example, MPI seek set. If you specify that for whence, then the file pointer is just set to the offset. MPI seek cur interprets the offset as a displacement, as an offset to the current position of the file pointer. And MPI seek end interprets offset as relative to the end of file. So, for example, if you want to read the last 1,000 elements at the end of the file, you would specify MPI seek end and an offset of minus 1,000. You can request the offset of an individual file pointer by MPI file get position. and you can get the absolute. Remember that this offset is always given in units of the E-type. If you want to convert that to the actual byte position within the file in order to do some reinterpretation or do something else that's not directly related to MPI-O, then you can compute the actual absolute byte position by MPI file get byte offset. So here you specify the file handle, the offset that you just computed with get position, and what you get is the displacement as a byte displacement with the data type of MPI offset. Shared file pointers are a way to read data collectively and have every single rank advance the file pointer as needed. So the simple call here is MPI file read shared. There's only one shared file pointer now, and of course, all processes must have the same view. It doesn't make sense if processes do not have the same view here. Individual file pointers, if you have them in the file, are not affected. So you can actually mix access via individual and shared file pointers in the same program. And if you access via shared file pointers, the shared pointer is a totally different entity. It's separate from the individual file pointers, and they do not influence each other. If you use it in the way shown here, then the ordering is not deterministic. This means that if many processes call that read shared function, which is not collective in the way I've shown here, then you don't know which one goes first and which one gets the first chunk of data. If you need that, you use the ordered version of the call. It's collective. If you need a deterministic mapping of the file content to the MPI rank. So finally, let me conclude with some examples and use cases. Here's an example that's actually representative of a large class of application scenarios. Our task is to read a global matrix of size 20 by 30 elements from a file in parallel. What we want to do is we want to view this global matrix as a contiguous data structure, but we want to store subarrays of that global matrix into a local array on each process. Now, of course, we need to specify in this case a distribution scheme, and I'll come to that immediately. So the distribution scheme is two-dimensional, so we need block sizes in either direction. There will be a data structure called L-array, which is the local array in each MPI process. So this is where each MPI rank stores the data that is part of the global matrix. Of course, this is a subarray of the global array G array, which actually never exists in the main memory of any computer, of any process. It only exists on disk as a concept, for example. So remember, the contiguous indexing is language dependent. We're going to be using C and C++ here, where all the indices start with 0. So here's our global matrix subarray, global matrix. It has 30 by 20 elements in C, numbered from 00 to 1929. And of course, in C, contiguous indices on the file in memory go row-wise because C has row major storage. The process topology chosen to distribute the ranks across this data structure is a 2 by 3 topology. So we assume we have 6 MPI ranks, and each rank should access a 10 by 10 subarray of the global matrix and store it into a local array. Of course, we want to do this as painless as possible for the programmer. So what we want to do is set up file views that let each process just read contiguously, or at least it should appear to read contiguously from the file, and end up with exactly the information, exactly the subarray it wants to read. Here's the code. We need to reserve space for the local array, which is 10 by 10 on each process, and we need to set up some MPI offset variables here, and I haven't gone through the hassle of actually declaring all the arrays. You'll get the drift. So first we need to create the virtual topology, because this is a Cartesian topology with 2 by 3 ranks. So the P sizes array has 2 elements as specified by NDIMS. The first has the value of 2, the second value of 3. So this says we have a 2x3 process grid, which is non-periodic in either dimension. That's why we preset the period array with zeros. And then we create the new communicator, MPI card create, from MPI com world, and com is our new communicator. We get hold of the rank of each process using MPI com rank, using the new communicator as a communicator argument, and the card coordinates. This is the actual Cartesian coordinates of our rank within this new communicator, and we get it in the coords array. Now we have to create a custom data type that lets each process have the proper view on the global array. The G sizes array stores the leading dimension and actually the size of the original data structure, while the L sizes specifies the size of the subarray, which is 10 by 10, of course. The starts array stores where in the first and second dimension the defined subarray should start. And it's, of course, coords times L sizes. So this sets a starting point within the global array for each individual process. And then we call MPI type create subarray to make this view on the global array a new data type, and we commit it using MPI type commit. Finally, we open the file with MPI file open. We want to read it. We don't specify any info object, and we get a file handle. We set the view to the just constructed data type, S type. The basic data type E type is MPI double, and we choose the native data format. Of course, we could also choose external 32 to make sure that this file is actually readable and writable from non-MPI programs. And then we use a collective read call, MPI file read at all, which is explicit offset. That's what the at says, and all makes it a global operation. The offset has been computed before. The L array and L sizes times L sizes 1. This is how much data is to be read, and again MPI double is the elementary type. What we get back is the status, and of course in this case it's not relevant because we can assume that the original data size on disk was as specified 20 by 30, but if we want to repeat this, for example, with individual file pointers, then we would have to check whether we have read the appropriate amount of data. So, as I mentioned, all MPI coordinates and indices start with 0, even if you're dealing with Fortran. And the indices may differ from Fortran indices, but here we deal with C. And here's the distribution on a grid of 2x3 processes. The names of the data structures that are used here correspond to the names used in the program on the previous slide. Remember, the G array doesn't actually exist as a data structure. It's actually the stuff that's on disk. All that exists as a data structure is the L array. And of course, in L array, the indices that the program accesses are always 0 to 9, okay? Because we chose the size of the local array to be fitting to the amount of data read from the file. I try to use colors here to indicate which values correspond to each other. For example, starts for rank 3 starts is set to 10 and 0, and these are the starting indices across the within the respective dimensions in the global array. For example, if start is 10 and 0, it means we're accessing the global array starting from index 10 in the first dimension and 0 in the second dimension. If starts is 10 and 20, we're starting to index the global array from 10 in the first dimension and 20 in the second dimension. All the mapping from the global array that exists on the disk to the local array is done using internal MPI-IO magic. So I think this is a very convenient and powerful way of accessing data. So in closing, I'd like to show you 2 or 3 MPI I/O application scenarios and how you could solve them or how you could handle them in practice. So one typical scenario is that each process has to read the whole file. And a simple solution would be just to use the blocking call MPI file read all. This is collective with individual file pointers. And since each process has to read the whole file, we can just use the same view on all processes, whether or not you're using the standard view or whether you want to use individual a custom-made view based on the E-type. That depends on what you want, but this is the standard solution for every rank has to read the whole file. If this is a performance-sensitive operation, then you may change to non-blocking semantics. So for example, MPI file read all begin and end. This is a collective operation with individual file pointers, so it's very similar to solution 1. However, it's non-blocking, meaning that the operation begins at the begin call and ends at the end call. So it's very similar to a non-blocking MPI point-to-point communication, but with the added benefit that you don't have to deal with any request handles and check them for completion. This is done internally, and yeah, it's quite convenient if you only have to do one pair of begin and end. And by the way, it could have the added benefit of doing asynchronous I/O in the background. Scenario B is about a file that contains a list of tasks. So for example, you could have a list of tasks. Each task requires a different compute time. So we want to read these tasks from the file and then have an automatic load balancing. So whenever a process doesn't have anything to do anymore, it reads the next task from the file. And that could be like an automatic load balancing mechanism like we investigated with the ray tracer program that was part of the exercises. In that case, you would like to use a shared file pointer using MPI file read shared. This is non-collective, so whenever a process calls MPI file read shared, it reads the next elements from the file. The shared file pointer is advanced, and then the process after that will read from that position. So this is non-collective. In scenario C, we have also a list of tasks in the file, but each task requires the same compute time, so there's no load balancing issue. In this case, we may want to use MPI file read ordered. So this is collective with a shared file pointer, but the order in which the file is accessed by the different ranks is predetermined. So rank 0 will always go first, rank 1 will go second, and so on, so that the mapping of file content to rank is specified and is ordered. You could also use MPI file read all with, that's a collective call, with individual file pointers. And then, of course, you would want to use different views to give every single MPI rank its view only on its relevant work tasks in the file, so that no MPI process has any way to read the task from other MPI processes. That would be probably a little bit over the top, a little bit too complex for this task, but it is one solution to this task. Now, one quick word about MPI error handling. File handling has its own error handling capabilities, so it's separate from the error handling for pure communication calls. The default with I/O is MPI errors return, which means I/O errors are non-fatal. In message passing, errors are fatal, so if you don't do anything about it, if an error occurs in message passing, your program will crash. The default file that is taken if you don't specify anything is associated with the special handle MPI file null. In message passing, it would be something like MPI com world. Now, you can change the default for these two parameters after MPI init was called by MPI file set error handler. So here, for example, we specify that the MPI I/O errors should be fatal as opposed to the default, which is MPI errors return. So this is how you say that if anything happens, anything bad happens with the MPI-IO, then the program should be terminated. After the first erroneous MPI call, MPI's status is undefined according to the standard. But again, according to the standard, a high-quality implementation will support I/O error handling facilities. So a high-quality implementation should give you the possibility, the option to establish proper error handling without messing up the internal state of the MPI library. So wrapping it up, MPI-IO has a very rich functionality supported by different data representations and access options to files. So it's really, really flexible and portable. MPI-IO has collective I/O routines as well as individual non-collective I/O routines. So if there's the option or the program semantics allows for collective I/O, you should actually use it because it might be able to improve I/O performance, since MPI has the option of eternally optimizing the access when the routine is collective. Actually, the situation is quite similar to the message parsing part of MPI, where also if you do something that can be mapped to a collective, then you should do it to give MPI the option to optimize what's going on in the background. All major MPI implementations have MPI-IO available and implemented. So you don't have to worry if your program uses MPI and you go to any system with a more or less standard MPI implementation, then MPI-IO is available. However, there's one caveat. Often, the proper use of MPI-IO is limited to special file systems. So for example, on many smaller clusters, all you have is your NFS-mounted home or scratch file system, which is shared across all cluster nodes. And if you use MPI-IO without checking that it actually works, you can get very surprising results, including data loss and corrupted data. So the underlying file system infrastructure has to be compatible with MPI-IO. If you don't know that, ask the administrators. Thank you.